Hello, welcome. I'm Errichto, and I want to welcome you to the first of two streams, lectures, about the expected value and summing some things in competitive programming problems. Today also it's an experiment because for the first time I'm trying to stream for both YouTube and Twitch at the same time. Also this time you should be able to see chat above my head, somewhere around here, in a video. I think it will be helpful, especially because we are on two platforms now. And yeah, we will start by covering the expected value. The only thing you should know already is what is probability, and I will show you the definition of expected value and how to use it. And we'll go through first for maybe an hour through some quite easy problems about the expected value. Then we'll move to the problems about the contribution technique that is kind of connected to the expected value, but not very tight. And both of these topics are to cover on Monday in second stream. Harder topic, that is some, let's say, dynamic programmings with expected value that require both these parts. If you want to see the materials that you see right now on the video, you can go to the Codeforces link that is provided in the description below. Hello William, hello Vibvav, sorry if I mispronounced your name. And let's start. Let's say with some example, if you buy a lottery ticket, for example, lottery ticket costs you, I don't know, $10. This is cost, so price of ticket, and let's say that with some probability, with probability 5%, you're going to win $100, and also with probability 1%, you're going to win $200. So it's quite easy to calculate how much you will earn on average, because it will be 5% times 100. So on average from this you get $5. This is 0.05 times 100, plus from this on average you will get $2, because every 100 time on average you'll get $200. And this is equal to 5 plus 2, yeah, am I correct? Yeah, to $7. So if you on average earn from this coupon ticket $7, then you shouldn't have, of course, bought it for $10 because it isn't worth it. But the kind of intuitive thing that we cover here, that we calculate here, is called in maths expected value. So this $7 is the expected value of the winning amount from this ticket. And the exact definition you can see here is the expected value of some event or experiment, for example, roll of dice, or like here, how much we win from a ticket in lottery. Is to calculate it, we should iterate over this small omega, that is an event possibility, and we should find the sum over probability of this event times the result if this happens. For example, here we had probability 0.05 times, then the result is 100. And this is how we compute the expected value. For example, if we roll a die that has 6 sides, with on sides it has 1, 2, 3, 4, 5, 6 pips, then the average result is 3.5. And how to calculate it? Well, it's one way is to just say it's an average of the 6 possibilities, or we just say from this formula it's 1/6 probability of getting 1 times 1 plus 1/6 times 2, and so on. So the probability, the expected value, is 3.5. Your title is still "This is a test stream, you can ignore it." Alright, so it should be. I tried to do things a little bit more automatically. So in the top of the screen you can still see some small, like, short title to help you if you later want to watch a video. This way it will be easier for you to know to what point you want to jump. For example, well, we will cover problems in order 1, 2, 3, 4, 5 and so on. So it will be easier to find some timestamp. But I tried to do it more automatically to read from a file, but I didn't manage. Okay, anyway. So if we roll a die, then the expected number of pips is 3.5. Okay, what about rolling 2 dice? So we roll a die once and second time, and what is the expected value of the sum of 2 scores? Well, it's 3.5 plus 3.5. And generally this the reason why we can add it like this is called linearity of expected value or linearity of expectation, and it's the single most important theorem in this topic. And it just states that the expected value of sum of 2 results is equal to the expected value of the first result plus the expected value of the second result. And what is important here is that we can always use this formula, always. Some theorems, some lemmas require the fact that the 2 events are independent. For example, the product of the results. But here, no matter if these events are independent or they're somehow correlated, you can always add it. And we'll use it a lot of times today. And the second technique we will be covering today is called, well, it doesn't have a certain name, it's contribution to the sum. Let's call it contribution technique. And in the second part of this lecture we'll cover it. There are some problems for that. And generally, if you want to find the sum over all possibilities, for example, we are given a sequence of numbers and we want to iterate over the subsets of these numbers, then we can iterate over each element in the sequence and consider how many times it will appear in the subset. Well, in this case it would be 2 power 9 minus 1. So for every element, how many times it would appear in the subset. And this way we count how much it adds towards the answer. So what is the contribution of this element to the answer? And also it might be reasonable to iterate over a pair of elements or an edge in a graph, and we will see that. Do those variables need to be related? Yeah, they can be independent, they can be dependent on each other, correlated. I'm going to an interview test. Okay, good luck, Rishabh. So let's start with problems. And first, if we have a deck of cards, so 52 cards, it's like 13 figures and 4 colors, the standard deck. If we choose one random card, then what is the expected value of aces in this one card? This is a very easy question because the probability that it will be an ace is 1 divided by 13. So this is probability. Because there are 13 figures and the probability for each of them is equal. Or you can say that it's equal to 4 divided by 52. Because there are 4 aces and 52 cards. And the expected value is also equal to 4 divided by, as well, 1 divided by 13. So similarly, if you for example, toss a coin, then the probability for heads is 1 second, and the expected value of heads in one toss is also 1 divided by 2. 13. Okay, what about here taking 10 cards at random? So if we take a card, then put it back in deck, reshuffle, then again take a card, put it back in deck, reshuffle, and so on 10 times, then of course the probability for each ace is 1 divided by 13, so the expected value will be 1 divided by 13 times 10. And the important thing to understand is that if the statement says that from a deck of cards we take 10 cards at once, we also can do it like this. It's also, so in fact it isn't just times 10, it's 1/13 probability in the for the first card, plus 1/13, plus and so on, plus 1/13. So this is probability that the first card will be ace, this is probability that the second card will be ace, and so on. And you might say that if the first card is, let's say, ace, then this card will be ace with probability 3 divided by 51, because only 3 aces are left in the deck. But we don't want to cover all possibilities. What if the first card is ace? What if it's not an ace? Because it would be quite complicated. But what we can do is here to say, not caring about other events, so about the first card or the remaining 8 cards, what is the probability that the second card will be ace? If you don't know what is the first card, well, it's 1/13. You can ignore what is the first card and you can say, well, it's the same probability as for the first card. Like, the order of taking cards doesn't matter if deck is already like shuffled. And so this is that theorem about linearity of expected value. We can add this even though these are not independent events. So for the first problem in Codeforces, we choose 10 cards at random from a standard deck of 52 cards. The answer is 1/13 times 10, simply. So it's 10 divided by 13. What does e of x plus y mean intuitively? Well, it's a good thing to try to read it out loud. So e of something means expected value of. And for example, e of x would mean the expected value of x. For example, the expected value of the number of, I don't know, the total number of pips when we roll a dice. And x plus y means just the expected number of something here plus the expected number of something here. For example, we can say that so those are not necessarily like numbers on a dice or in cards. Let's say that we are worried about the expected size of rain. Well, for something like the expected number of centimeters per square meter, something like that, or liters times per square meter. So this is something that you can see in the weather forecast. And also you can see likely something like expected strength of wind. And so let's say that the expected rain is, I don't know, 5 centimeters of like height, and expected wind is, I don't know, 10 kilometers per hour, something like that. So this is 10. And of course here it's a bit stupid to give this example because the units are different, but let's say that this is the expected size of rain in this centimeters height, and here is the expected strength of wind in kilometers per hour, and we can just say that the expected rain plus wind, it's important to read it. What does it mean? The expected value of total rain plus wind. So we wonder, what is this value? It's like, let's say that the weather forecast wants to just tell you what is like this value, this sum. And the theorem says that even though wind and rain are correlated in some way, we can add it. And we say that, well, we should, if you want to bet what is the value of this thing, I don't know why you would bet that, but the expected value of that, the average value of that is 15. If we choose 10 random cards, then 10 divided by 13 will be aces. Yep. I love this explanation of x plus y. I'm glad you liked it. Okay, and now the second problem. The price of a TV is $1,000, and then there are n days, and each day the price goes up, either by $5 or by $10, each with probability 50%. Find the expected value of the final price. Well, we can say that, so let's go back to drawings. So the value after 1 day will be either that 1000 plus 5 or 1000 plus 10. Then it can be again plus 5, plus 10, plus 5, plus 10, and so on. So actually you can draw a binary tree of possibilities if you want, because there will be 2 power n possibilities, like what happens. And some approach for that is some dynamic programming or binomial coefficients, if you realize some fact. We'll get to back in one of problems later. But actually we can say that the final price is the like the initial price plus delta in the first day plus delta in the second day and so on, plus delta in the nth day. And we want to know the expected value of this. And well, what we can do is we can find the expected value of the change during 1 day. So in second day, the expected delta, the expected amount it goes up, is 7.5, because it goes either up by 10 or by 5. So the average is 10 plus 5 divided by 2. And this is also equal to the expected delta in the second day and so on. And since we can use the linearity, the expected value of this sum is the expected value of 1000 plus the expected value of delta 1 and so on. So we can say that the answer is 1000 plus 7.5, 7.5 and so on, 7.5. And this is the answer. Yes, exactly. So congratulations to those who also solved it. There's a bonus if maybe we'll cover that on Monday. What if the price goes up by 1 or 2% each day? Then it's something different, and so far we will not cover that. Okay, the next problem, third one. Okay, I forgot to change the title, so let's move to 3. Max of 2. Since problems right now are quite easy, I will not change it for every problem maybe, but it's still enough to binary search a good moment. Max of 2. You roll a 6-sided die twice. Find the expected value of 2 scores. And there are quite a few possibilities for that. So a new sheet. Well, maybe this one will be useful, or maybe not. Let's go with blank one. Okay, so we can so we roll a die twice, and there are some possibilities. The scores can be 1-1, 1-2, and so on, 1-6, 2-1, and so on. And it's quite hard to write all of that down. So it's better to write that in a form of table. So this is the first result. This is second result. And we can draw a table like that. And so so here we say that this cell represents result 1-1. Here, let's say 1-2, 1-3, and so on. So this is result. This is result in the first row. This is result in the second row. So each of these cells has probability of 1 divided by 36. And there are 36 possible cells. So this is 1/6 times 1/6. And we can in every cell write what is the score. So what is we are wondering about the expected value of the bigger of two scores. So this thing is what we want to count, the bigger of two scores. So here the bigger value is 1, here 2, 3. So for example, if we score 1 and 3, the bigger one is 3. And we can write that in every cell, and so on. And here we can count. So what are the possibilities here? The most stupid one is to just sum everything up. So there is 1/36 probability that we'll get 1, plus 1/36 that we get to here, plus 1/36 that we get to here, and so on. But this is quite a long way, so let's not do that. Okay, so every possibility here is equally likely, so we can take average of that, and we can just find the sum of these 36 values. Something like 1 plus 2 plus 2, 2, 3, and so on. And instead of just writing down all the numbers here, let's just count how many 1s appears, how many 2s, how many 3s, and so on. So what I claim is that there is one number 1, 3 numbers 2, 5 numbers 3, and so on. And numbers 4 here, it will be 7, and so on. Every next number has 2 more occurrences. So, and eventually 6, I think, has 11 occurrences. And we can sum this up, and we'll get the answer. So this is the expected value of the bigger score. Still, it isn't I think the shortest possible solution, and we'll see, I think, 2 more ways. Good follow-up problem will be little pony at expected maximum. Yeah, let's try to go from easy problems to hard ones. So let's do something different. We said at the very beginning that the definition of expected value here is the iteration over the possible events. So we iterated over 36 possible events of this sum. But what we can also say is that it's the sum over possible, let's say, answers, I don't know, R, over probability to get the answer R times R. So this is basically the same thing as that first formula, but this interpretation, this representation allows us to solve this problem a bit easier. because we can say that the probability to get number 1 here is 1 divided by 36. The probability to get number 2 is 3 divided by 36. 5 divided by 36. And so on. And the sum of these, 1 times 1 36, 2 times 3 36, and so on, is the same thing as we had earlier. So yeah, this is some alternative. So we iterate over the result, R. Here result can be from 1 to 6. And we sum probability of this result times result itself. You can notice that for rolling a die once, we get exactly the same thing as the initial definition, iterating over events. Okay. Shouldn't the delta 2 be... so you're asking about the previous problem. No, in the second day the price goes up by $5 or $10, so on average it goes up by 7.5. The previous day doesn't matter there. Okay, and also one smarter way to count these probabilities without looking at the grid is to say that the probability of getting, so let's erase that, the probability that will be somewhere here, so that the results will be up to 3 is simply 9 divided by 36. In fact, it's 3 divided by 6 square. So once again, 3 divided by 6. This is probability that we will get at most 3 in a row, and we want to do it twice, so square. So this is probability that we get at most 3, and if we subtract probability that we get at most 2, so minus 2 divided by 6 square, we'll get the answer, and it will be the same. It will be 9 minus 4, so 5 divided by 36. And actually, I think someone commented here a problem about it, Otalyptus commented it, where a problem says that dice has m faces, not really 6, and we want to compute the same thing. And if you take a look at the editorial here, you will see that again they consider probability to get this maximum score, and it will be I divided by 5 to power n minus I minus 1 divided by 5 power n. So back here, so generally the probability to get answer R, so the bigger score will be R, is here R divided by 6 square, probability that we'll get at most R, and minus probability that we get smaller numbers, so R minus 1 divided by 6 square. And and here instead of 6, of course, we can put something else, and here if we have more than 2 rows, we just put the number of rows here, and this is probability to get exactly R as the maximum. So we can, so from this formula we should find the sum over R times the probability here. Okay. So this was second approach, and there is a fourth possible approach, or third, I don't count. Also, we can count the probability that the result will be bigger than something, and simply find the sum of those probabilities. So this is a very short sentence and explanation, and I think we'll cover that more on Monday. So anyway, we see here that there are quite a few solutions. And the next question was max of n. So we roll a die n times, and then the difference is that here instead of 2 we'll get n, because now this is probability that in r rows every time we get number up to r, like r divided by 6 is probability for one of numbers 1, 2 and so on up to r. Okay. And I said here that there are quite a few solutions. So I didn't put a limit here, a constraint for n. And what if it's an actual problem and we want to print the answer here? So n is up to something. Well, if we want to compute this power thing, then we can use C++ function, and it will be more or less constant. If we want to implement it ourselves, it will be log, and it isn't a big deal. But if we don't see this observation with powers, one more idea is to compute dp of 6, where dp of something, for example dp of 3, will be probability that so far we'll get maximum of 3. Well, here we can add one more dimension, it will be n, so the number of rows that are already there, n, and this should be also with n. So when we already considered n rows, what is the probability that the maximum will be 3? And with 2 loops we can calculate that, because when we know, for example, that the probability of with 5 rows to get maximum of 3 is something, let's say that it's 0.002, whatever, then from this we'll consider every possible next row. So maybe we'll get row with 1, 2, 3, so 4, 5, 6. So what is the next possible result? And then we know what is the new maximum. So dp, now we move to dp n plus 1, and here the new maximum, if we had maximum 3 and a new result is 1, then maximum is 3. From 2 we also got maximum 3, here 2, and here we have n plus 1, and maximum is 4, and so on. This is a simple dynamic programming. Okay, and if n is huge in the problem, for example n is up to 10 power 9, one complicated approach is matrix explanation, and the second thing is to notice that, well, we can just print 6 for big N. If we roll a die, for example 1000 times, it's almost impossible that there will be no 6s. So the answer will be something like 5.9999 and so on. It will be a lot of 9s, and since usually we are asked to print the answer with some precision, we can just print 6 if n is bigger than maybe 100. So in case you invent just this dynamic programming approach and you want to make it fast, then you don't have to care about big N. And one more thing. Hello, no moniker. One more thing about it is, well, we will talk about it in a moment in problems about coins. And now we move to birthdays. Let me change the name. Birthdays. So the problem is, there are 20 students in your class. Let's say you're teaching them informatics, and when someone has birthday, they ask you to just play games instead of learning informatics. So every day during a year, if someone has birthday, maybe 2 people, they play games instead of learning. And well, let's say that otherwise the classes are every day. So there are 365 days during a year. And now, possibly if many people have birthday on the same day, then you will not waste 20 days during a year. Instead, maybe 19 or 18. So the question is, what is the expected number, the expected value of the number of wasted days? So wasted meaning at least one student should have a birthday. Okay, so the number of days is 365, let's say, it's a standard year, and there are 20 students. And now, okay, what are possible approaches? One of them, similar to what we covered a moment ago, is to try with some dynamic programming over day and the number, so day we already considered, and the number of students we already considered. So for example, you go day by day from 1st of January, so from day number 1 or 0, and you consider what is the probability that so many students are born this day. But this is a complicated approach. We will not do that. Instead, what we can do, well, we should, what about thinking about one student? If we count for one student, what is the probability that he is the only one with birthday on some day? It isn't enough for us, because so the thing is that if you want to approach it from the side of a student, to say what is the probability that he has birthday with someone or he has birthday alone, to know if he creates a new wasted day, the thing is that we also should care whether 3 or maybe 4 people have birthday on the same day. It's not very likely, but it's also possible that 3 people have birthday on the same day, and then it's quite hard to compute that. And here there is an easier approach. Please give some time to think about problems before saying the answer. So this is why the problems were posted before in Codeforces. Some of these problems, so you could think about them earlier, if you prefer that. Some of these problems are very important. For example, for sure, some problems from the second part here, and then I will indeed give you some time, like 2 minutes, to think before me showing you a solution. But here we just want to go through these expected value problems. Also, if you don't get some of that, it isn't very bad for the second part, because they aren't very connected. But you should try to understand all of that before the Monday stream if you want to then be up to date. Okay, so an approach from the side of student is wrong, but we also can approach it from the side of the other thing that we have here. So we have 2 things here. One is day and one is student. And we said that from this side it's hard to approach, because we also would have to consider the fact that maybe he has birthday with 2 more people or 3 more people, and it's hard to compute. So we're not doing that. And the second possibility is to do something from the side of day. So we're computing something from each day, for each day. And actually, if you remember about our linearity of expectation, you know that so the expected, we said a long time ago that the expected number of aces, if we draw 10 cards, is just 10 times probability of ace. And we should use the same here. It's actually a similar problem. The expected number of days with birthday is equal to the number of days times the probability of day with birthday. And it's from one side it's very counterintuitive that those days don't interfere with each other because they are dependent. If you know that someone has birthday on 1st of January, then the probability for each another day is slightly slower because you're only left with like 19 or 18 students to distribute there. But the linearity says it doesn't matter. We can always say that the expected value is the sum of the expected values. So here actually from the formula this is expected value of the number of days, such days, along just one day. And in other words, it's just probability that this will be a day with birthday. So this will be the answer, and we just need to compute this probability. And actually here again we have a fact that it's hard to compute probability that 3 students has birthday or something like that, but it's easier to compute probability that there is no birthday, because the probability of no birthday, well, if we are just looking at one day, for example 1st of January, what is the probability that student number 1 doesn't have birthday on this day? Well, it's 364 divided by 365, because he should be born on one of other days. And there are 20 independent students. When we talk, so this is more probabilitics topic than expected value or contribution. In probability, if some events are independent, then you can multiply them. So here students are independent from each other. So probability that none of 20 students has birthday on this day is something like that. So now let's say that this is the number of days is m. Then this probability is m minus 1 divided by m powered number of students. So the probability of day with birthday is 1 minus that. So 1 minus this probability. And this times 365 is the answer. Errichto, consider you starting using Patreon. People can keep you more motivated to keep on doing these streams that way. I'm not really going to do it soon. I'm not struggling for money, so it doesn't matter much. Today will be this raised to the power of 20, exactly, Harsh. That was trivial. Well, we must go from some simpler topics to go to harder ones. Now some problems about tossing a coin. So maybe before that, do you have questions so far? So do you have questions regarding some of the first 5 problems, things we covered so far? Maybe I should explain something again. And if not, we will move to the slightly harder problems. Here I'm going to already prepare an empty page. And I guess there are no more questions, and we can move on. So the next problem is first heads. Can you go through the reasoning for problem 5 one more time? Okay, so quickly. So what we can calculate quite easily is the probability that there is no birthday on 1st of January. And the probability that one student doesn't have birthday then, so has birthday on one of remaining 364 days is something like that. And it must be satisfied for all the students. So this is probability that the second student doesn't have birthday and the 20th student. So this is this ratio power 20. So then probability that this day has some birthday, so the probability for wasted day from the statement is 1 minus that, because this, either this happens or this happens. And the linearity of expectation says that we can sum these probabilities for each day, even though they are not independent. So the answer will be this for 1st of January plus the same for 2nd of January and so on. So the answer will be the number of days in the year times the probability of wasted day. Okay, and now problem number 6. So the problem says you are tossing a coin until you get heads. What is the expected value of the number of tosses? So how long on average you will have to toss a coin till you get heads? So there are again quite a few approaches. One is to write down some possibilities. For example, we can get heads immediately in the first toss, and then so the probability for that is 1 second, and in that case we have exactly one toss. This is result. Also, maybe in the first toss we have tails and then we have heads. The probability that this will be tails is 1 second. The probability that this is heads is 1 second. So the total probability is 1/4. And here the result, the number of tosses, is 2. Then maybe 2 times we'll get tails and then heads. So 1/8 times 3. And now maybe 3 tails before first heads, and so on. And the sum of these values is the answer, because it's from the definition of the expected value. And okay, and let's find this sum. There are a few ways. I think the nicer way, it's kind of like tricky maths, to write it down smartly, is to say that we want to sum 1 second plus 1/4 and again 1/4. So these are 2 1/4s plus 1/8, 1/8, 1/8 plus 1/16, 1/16, and so on. So there are pluses here everywhere. So of course here I just wrote the same thing in a different order. And if you write it this way, then you can see that this sum, it's quite known fact that this sums up to 1. Then this is the same without a half, so it's 1 second. It's just geometric progression. Or you can say that this divided by 2 would give us the same thing, because this divided by 2 is 1/4, this divided by 2 1/8, and so on. this is 1/4, then we have 1/8, and so on. And the sum of this, similarly, is 2. So the answer is 2. So it isn't very important to know how to do things like this, but I think it's a nice technique that you might learn in some advanced, like in some math lessons in high school for those who are interested in maths, like if they trained for competitions. Okay, and this is a correct result. Let's see if there are any questions. Keep s as sum, then you multiply by 2 and subtract these equations. Yeah, there are many ways to explain this, and if you have any sum, also a sum like this, you can say that this is equal to s and try to experiment with that, add something, subtract something to get an equation for s. Like, this is just a method that I like. Okay, and disadvantage of this method is that here we can skip some cases. We can forget about some cases. Of course, it was an easy example, but later we will see a problem where we want 2 heads in total. And then if you write down possibilities, like maybe it will be heads, heads, maybe heads, tails, tails, heads, and so on. Maybe tails, then heads, then some sequence of tails, heads. You can skip something. So a better approach, something that I myself don't really like, is to draw a tree of possibilities. So in the first row we have either heads or tails, then we have either heads or tails, and so on. So let's focus on this problem with 1 head. So here we end if we in the first toss got heads, and the probability for that is 1 second, and we end with score 1 with the number of tosses. Here the probability to get here is 1 second, and we must continue, and it will be either heads or tails. Here it's the end because we got heads, and the probability 1/4. Here 1/4, and we go on, and so on. Of course, it's not for you to draw all the possibilities here because it's impossible. The sequence is infinite. But it's a way where if you dismiss something, so if you say, okay, this is the final state because we got heads, then you can't really skip something unless you make a big mistake, an obvious mistake. So this might be a more mistake-proof way, but the logic, the computation will be the same. You will just see, okay, I have 1 second to get 1, 1/4 to get 1, and so on. Okay. What's wrong with p equal to half plus half times p? There's nothing wrong with that. And okay, so another approach is, let's say that r is the result, so that expected value. And okay, what now? There are 2 possibilities. So from the definition of expected value, we can say that we can iterate over possible events and find the sum over probability times result. And with probability 1 divided by 2, we get heads immediately, so the answer is 1. So this is heads in first try. And with probability 1 second, what is the situation? Well, we wasted one toss already, so we got tails. And what is here, what we can put is the expected number of remaining tosses. So this will be r. This is how we defined r. Because we can say, okay, we start from 0. Well, we didn't have any heads, so right now we wonder how many on average tosses we need to get heads. So you can solve just this equation for R, and you will also get 2. And so it's almost what Hadi Hadavi said. He just skipped +1. Yeah, I agree with Anton Lupanov. Yeah, and if you see an alternative solution, I guess a better question is whether it will work instead of what's wrong with this. Like I haven't said or implied that this solution would be wrong because I didn't say a single word about it. So here I just wanted to provide different possible approaches. And what about harder versions of this problem? So problems 7 and 8 are slightly harder. And problem 7 is, what is the expected number of tosses till you get 2 heads in total? Yeah. So you can do one of the 3 techniques we showed. So either write down possibilities, something like sequences like H, T, T, H, something like that, and find the complicated sum and solve it. Also, you can do that for a tree, and you can try to create an equation like this. Sorry. You can create an equation like this, and this time it's good to use the fact that we already know an answer for 1 heads, because if you already get so for example in the first toss, if you get heads, then you know that no matter what happens here, the expected value of the remaining tosses is on average 2. This is what we computed in the previous problem. And actually there is a very straightforward solution without any equation, just like in your head. If you know that you on average wait 2 tosses for the first heads, then after you get that, what is the average time you have to wait for the second heads? Well, it's the same thing. You just toss until you get heads. So this is expected value to wait for first heads. And this is the same for second. So if you know the answer for the first problem, for this problem the answer is just 2 + 2. And if you want to get 10 heads in total, the answer will be 2 times 10. Well, generally 2 times the number of heads you want to get. So this is expected value for n heads. Yeah. Because, well, no matter if the results are dependent on each other or not, we can find the sum. So because the expected value to wait for n heads is the same thing, well, the time, well, first without the expected value thing, the time you need to wait for n heads in total is equal to the sum. The time you wait for the first heads, second one, third one, and so on, plus the time you need to wait for nth heads. And linearity says we can add this up. So this turns out to be easy problem once you solve the simple one, the one for 1 heads. Will you finish in time for educational round? I hope so. So it's hour and a half, right? To the contest. Yeah. So we will try to finish like hopefully 15 minutes before that. We'll see. Okay. And problem 8, 2 heads in a row. is slightly harder, and let's leave that as a homework. If you don't know how to solve it, just on Codeforces you can leave a comment, or you can leave a comment there if you know how to solve it, to describe to others. So it's a similar thing, just more complicated. Here we ask about the expected number of tosses until you get 2 heads in a row, and then if you get tails, then the situation is like from the start, so you can create some equation again. But if you get heads, it's slightly more complicated, because you must consider, like, again, immediately you must consider the second toss. So actually it's good to draw like maybe a tree that considers possible situations in first 2 tosses, something like that. And we'll move to the problem number 9, volleyball. And let's see if there are any questions. Hello all, hello Mohit. Just in case it isn't clear, harder part is on Monday, but it's a part that doesn't involve these problems. All of these I'm going to cover today, both expected value and the contribution technique. But these contribution technique problems are quite easy. And on Monday, we'll just cover new problems, harder ones. So this will be something like Codeforces D or E difficulty. Okay, so we move to the volleyball problem. And in this problem, there is volleyball tournament. There are 12 teams, including, let's say, Poland. Teams are divided into 4 groups, each with 3 teams. Let's visualize that. Okay, so there are 20 teams. They are divided into groups of 3 teams. In each group, everybody plays with everybody. And in each group, from the group, 2 people will pass to the next stage, to the tournament stage. Maybe they will be shuffled, but it doesn't matter at all. And then they will play quarterfinals, then here they play, how is it called, half finals, and eventually the 2 teams play the final. Okay, and one of them is Poland. We say that in each team, in every match, a random of 2 teams wins. Each team has 50% probability, and there are no ties in volleyball. So initially I wanted to say that this is a football tournament, but it has an obvious disadvantage of having possible ties. So let's say that there are no ties. Well, in volleyball there are no ties, and each team wins with 50% probability. So teams are kind of symmetric to each other. So Poland isn't stronger or weaker than other teams. And also, in one group, it's possible that there will be a perfect tie. So in total, if first team wins with second one, then this team has a win. Then second one wins with third team, it has 1 win. And third team wins with first one, it has 1 win. So each team will have 1 win and 1 lose. And in such a case, we say that 2 random teams pass to the next stage, to the tournament stage. Okay. And what are the questions? Find the probability that Poland will win the whole tournament. Then find the expected value of the number of matches won by Poland, and then something else, something more complicated. So, probability that Poland will win. Well, teams are symmetric in one group. So, if from 3 teams 2 pass to the next stage, the probability of passing the group stage, and advancing to the tournament stage is 2/3. Okay, sorry. Now there is a quarterfinal, and Poland has 1 second to win that, then half final, have to win that, and the final. So the answer is, so this can be reduced, and the answer will be 1 divided by 3, 2, 2, 1 divided by 12. And either in the first moment when you see this question, or if you see this answer, you might notice a much easier solution. Yeah, William Lin said that in comments. Congratulations. 1/12 just by symmetry. Exactly. There are 12 teams. They are symmetric. No team is better than others, and one of them will win. So the probability for Poland to win is 1/12. And it's just a nice thing that you often use in probability or in combinatorics. So this is the probability that Poland will win. And now the expected, the second question, the expected number of matches won by Poland. Well, so in the group stage, there are 2 matches, and Poland on average will win half of that. So from group stage, we get on average 1 win. Now, with probability 2/3, we got to quarterfinal, and with probability 1 second, we win that, and we multiply that by 1. So this is 1 extra match won, and this is probability. This is probability that we will indeed win quarterfinal. So it doesn't happen if we don't advance from the group stage, and it doesn't happen if we advance but we lose in quarterfinals. Similarly, what is the probability that we win half finals? Well, we must advance from group stage times win quarterfinals, quarterfinals, times win half finals, and well, times 1. So this is 1 extra match won. And probability to win finals is this, what we, by the way, already covered. So this is 1/12 that we computed in the first part. And we can find the sum. I'm not going to do that, it's some number. Okay, well, maybe it's a good thing to compute that, because again we will do that in the same way, so let's see if it's correct. By the way, an alternative way to say what is this probability to win quarterfinal is to say that half finals, is to say that there will be 2 teams that will win some half finals. So Poland has probability 2 divided by 12 by symmetry to be one of those 2 teams. So let's do that simpler. It's 1 plus, this is 1/3 plus 1/6 plus 1/12, and this should be equal to, divided by 12, 12 plus 4 plus 2 plus 1, I think it's 19. So it isn't as easy result as here, but also there is a way to express that, to explain that without any computations. It's not 26, but yeah, it should be computed by symmetry. I think you miscalculated something with that 26. So Kumar Abhinav, how did you get 26? But yeah, it isn't a coincidence that here it will be 12. I think the number 19 is correct, not 26. Yeah, so what is the total number of matches in the whole tournament? Well, there are 3 matches in every group, so 12 matches in the group stage, then 4 quarterfinals, 2 half finals, 1 final. So in total there is 19 matches. And so the expected number of the total number of won matches, the expected value of the total number of won matches is 19, because it must be exactly that. And Poland on average will win 1/12 of that. I considered all matches, even those not played by a team. So yeah, it's correct, but I think you just miscalculated 26. There are 19 matches. Okay, and also so also there could be a question: what is the expected value of the so this was 1, and this is the expected value of the number of matches won by Poland. What about question with played? What is the expected number of matches played by Poland? So one way, of course, is to do it like here brutally, to just say that we play 2 matches here, then there is some probability of getting to quarterfinals, half finals, finals, and so on. We just don't consider here this last number every time to probability of winning this match. But we can also say that in total there will be 38. So the total number of matches that teams played is 38. And why is it 38? Well, because a match is played by 2 teams. So if we sum up the number of matches played by those teams, from one match we get 2 in total. Like every match has 2 teams. So this is the sum over the number of matches played by teams, and divided by 12, it would give us the average number of matches played by Poland, so the expected value. Yeah. So the answer for question, the expected value of the number of matches played by Poland is 38 divided by 12, so 19 divided by 6. And there is also 38 slots to play a match. This is very good interpretation, Anton. Thanks. So we can think about it as slots to play a match. So in every match there are 2 slots. So the average number of slots Poland will use is 38 divided by 12 by symmetry. And there is one last harder question. What is the expected value of the number of matches won by Poland, assuming that they won the whole tournament? And if you know probabilities, then this looks like conditional probability question. I'm not sure about the name in English of that. But we can rephrase that to be a bit easier. Find the expected value of the number of matches won by the winner of the whole tournament. This is the same thing that is said earlier. Won by Poland, assuming that they won. So in other words, expected value of the number of matches won by the winner. And then we know that the winners for sure won quarterfinals, half finals, and finals. And we also must compute the expected value of the number of matches won in the group stage, what is a bit harder, because we know that they must advance, and we just must consider all possibilities, what happened there, such that they advanced. So this is something you can go through in home. It can be solved just by symmetry, to say that it's something divided by 12. So here we must go through the possibilities. You can also say that with 19-12 wins and symmetric teams, you won half you played, thus you played 38 divided by 12. I agree. Yeah, Anton. So on average, we the number of wins is half of the number of plays, the number of slots, and so these consider options here are something you can do yourself later. And with that we move to the contribution technique. That is the essence of the lecture. And do you have any questions? And no matter if there are questions or not, I'm also going to take a 1 minute break, maybe 2 minutes, just to grab something to drink. If you discuss solution of Codeforces Div2 problem after every contest, it will be very helpful for beginner programmers. Yeah, I said that many times, that it's especially helpful if I talk about something that is not in Codeforces, because Codeforces has editorials. So this is why, for example, I talked about Polish National Olympiad that has quality problems but doesn't have tutorials in English. And yeah, sometimes I will cover problems from Codeforces rounds. In general, I will cover some problems from competitions. This is even more helpful in my opinion, says Gustav. Yeah, I think that this lecture is more useful than anything I did so far in this YouTube channel. I think that solving problems is cool, but there are editorials, and here you see an actual lecture about one topic and a hell lot of problems about this topic. So I think it's more valuable. Do you have some new ideas about terminal? Just have or not sure. No, I didn't have time at all for the terminal game. So for those of you who don't know, the terminal is a game where you're supposed to write a bot that plays a game, so a simple AI. And I did a series of lectures about that, lectures. I streamed me starting with this game, showing from my experience what should be done, what can be done, and I implemented something. You can watch that later if you are interested in writing bots for games. You can see it in my channel as playlist terminal creating AI bot. So the first part is quite easy. It shows the rules of games. And the last part is then quite hard, and there I create some quite complicated algorithm for graphs, something like harder BFS, but it allows our program to understand a map in some way. So we move from simple topics and from talking about intuition to actually implementing something hard. And the contest lasts till the end of the year, so you can still join. There are problems that can appear in, let's say, an Oxford interview, right? Oxford interview. I don't know anything about Oxford interview. I know something about interviews to some, I don't know, trading companies, to some big companies that so if you also apply to big company that like Google, but your job will be related to maths a little bit, then you should understand expected value probabilities. And if you apply just to a big company like Google, I don't know, Amazon, Facebook, you can expect some of these problems here, the contribution technique. Maybe not necessarily a problem, what is the expected number of tosses of coin till you get something, but the easier problems among those can appear. So actually one of the problems we will cover is from Google Code Jam Kickstart 2017, and this is a contest that helps them to catch like talented people and to hire them. So this is an example that it is useful when you're preparing for an interview. But I don't know much about Oxford interview. Thank you, Abudia, for nice words. And at what college did you study? University of Warsaw. So we move to the contribution technique problems. how is it called? Hills. And let's get back to the definition or something. Well, this isn't something very formal. I don't know an exact name for that. I think the best name I can think of is the contribution towards the answer, towards the sum. And if we are to find the sum over some ways, then we iterate over an element and we count how many times it will be added in the sum, in the answer. And while this explanation might not be very good, let's see problems for that, and then I think it will appear more clear what we should do. And the first problem, hills. Given a sequence of numbers, size 100,000, count triples of indices that create a hill. And hill is 3 indices such that the middle value is higher than the other two. So some 3 indices I, j, k, such that this value at j is bigger than the other two. And it doesn't matter whether the other two are first is bigger than third or the other way around. Okay, and this problem can be solved with divide and conquer in some quite complicated way. We will not do that. And also it can be solved in some other way that you can think about later, and I put a bonus here: count zigzags of length 10. So tens of indices such that the value alternates, it goes up and down. For this you need a different approach, but this first approach, this first version, has an easy solution with the contribution technique. We want to count the triples easily, and for that we'll iterate over each element, and we will count how many times, how many triples it creates. Here it's hard to say for some considered number AI to count how many hills it creates, how many times we have a bigger number to the right and then even smaller number somewhere to the right. Also, please note that the 3 indices don't have to be consecutive. They don't have to be adjacent in the sequence. Here it's better to iterate over the middle element in the triple, aj. And then, if you iterate over this middle element, you just want to know how many smaller numbers are there to the left and how many smaller numbers are there to the right. For example, if the sequence is 2, 3, 8, 5, 3, 7, 1, 8, then if we take a look at number 5, in how many triples it is as the biggest value? Well, the left value can be 2 or 3, and the right value can be 3, 1 or 4. So it creates L times R possibilities. Here it's 2 times 3, so 6, where L is the number of smaller values to the left, and R the number of smaller values to the right. So this is the number of triples where this element is the biggest one, so the middle of the 3. And we can just find the sum over these values for every element considered as the maximum value. In solutions like this, we must be careful whether we don't count some possibility twice or more times, but here it's okay, because every triple that we should count has exactly one middle element maximum. And a few words about implementation. If you want to count that for every number, to count the number of smaller elements to the left and the same thing from the right, the best thing I think is to go from left to right. I think we can call that sweep line, maybe, and to put the numbers in some segment tree. maybe we must first scale them. So if the numbers are from 1 to 1 billion, then only the order of numbers matters. So we can scale them to 1 to n. So like to put, if for example numbers that appear are 10, 15 and 20, we can change that to 1, 2, 3, right? And the answer will not change. But this is not very important. There are some ways that you can do that, and here today we want to focus on the contribution technique, not on implementation of this problem. And so this is a correct solution, and it works in n log n. The second problem. So second problem is extremely important, and here actually I will give you a moment to think about it. Just first let me change a name. Paths in tree. Given a tree of length 100,000, find the sum of lengths of all paths. And there are some ways, some solutions with not really easy dynamic programming or with centroids, but here it's about a very simple solution. So I'm going to give you a moment for that. Don't spoil the solution immediately in the chat. Using set is simpler than segment tree, but you must use set that is able to say how many numbers are smaller than something. So it's in C++, it's possible to include such a set, but it's like more complicated. So try to think a moment about this problem, and I will draw an example. For example, for this tree, there are 8 paths with length 1. So this path, this. Now there are 1, 2, 3, 4. 4 paths with length 2. Then 2 paths with length 3. And I think that's it. Right. 2 paths with length 3. So the sum of lengths is 4 times 1 plus 4 times 2 plus 2 times 3. 4, 8, 6, 18. And this is the answer. And try to think what is an easy way to solve this problem. Using the contribution technique. So for every something, we want to count how much it adds towards the answer. How many times it appears, it should be counted. So 1 minute to think. And not yet the full solution, but how to approach that is, so previously we iterated over the middle element. Here what we should do is we should iterate over an edge. For each edge we will want to add something to the answer. And so one simple part is to say what we want to add. Like for each edge we want to add what number of things to the answer, and the second thing is how to compute that. And let's hear a solution. So every edge, well, you can think about it as something that has cost of or length 1, it doesn't matter much, but this length of 2 also can be say as 1 plus 1. So like each edge adds 1 to the answer for each path that it is in. So actually we can say for each edge to the answer we add the number of paths that contains this edge. Because we can say that if we have, for example, this path of size 3, then this edge is counted once in the answer, this edge. So for every edge we count in how many paths it appears. So what about this edge? Well, the beginning of this of the path that goes through this edge, so the left end can be either here or here, so 2 possibilities, and the second, the end, can be here, here, or here, so 2 times 3 possibilities. Okay, and generally for every edge the number of possibilities, the number of vertices here, so one of those must be one end, and the number of vertices on the other side of the edge. And if with very simple DP we compute size of subtree, for every edge, so just going from bottom to top once, bottom up once, then if we here know that the size of this subtree is 3, then to the answer we must add 3 times n minus 3. This is the number of vertices not in the subtree. So we iterate over every vertex, and then we want to consider the edge going from this vertex up to the parent. Of course, then we don't consider the root itself, because there is no edge here. Okay, and we find the sum of the size of subtree times n minus size of subtree. So for every edge we counted how many times it was counted in the answer. And this is the very important thing. This is the solution that we should think about when solving similar problems about this technique. Something like number of nodes in subtree of a node multiplied by the rest of nodes. Exactly, Manjit, Kumar, the same, yeah. Even if a tree is not rooted, we can root it in just, let's say, vertex 1. Oh, sorry. It doesn't matter much. Just root it in any vertex, so you could find the sizes of subtrees. We do it so that for every edge we would know what is the number of vertices on both sides. And this is a very simple solution for this problem. The bonus problem, if you want to think about someday, is find the sum over squares of lengths of paths. Then it's like a bit more complicated. I think the easier solution will be some bottom-up dynamic programming. It won't be the same type of solution, so we will not cover that. And so when you think about the contribution technique, think about this problem and try to do something similar. So we move to the problem number 3. But first, since this is the single most important problem today, I think, do you have questions for this problem? And if not, we'll move to the third one. Okay, so we will move to the third problem, sum over subsets. And it's an easy problem, but it shows how to approach the next two problems. Let me move this thing a little bit to the right, because Firefox name is apparently a bit long. And okay, sum over subsets. So there is some story here. There are n competitions, programming competitions. The ith competition has prize AI. You're a very good programmer and you will win each competition with probability 50%. Find the expected value of the total won prizes. Can you do a quick recap? You can rewind the stream to or look after. Well, so once again, very quickly, every path to the answer adds the number of edges in this path. So for every edge in a path, it adds 1 to the answer. So for every edge, as many times as there is a path that contains this edge, 1 is added to the answer. So it's enough to count paths going through this edge, containing this edge, and add this number to the answer. And this way we will also get the same thing, 18. Here, so for this edge it will be 1 times 4, so here added will be 4, here added will be 2 times 3, 6, here added will be 1 times 4, 4, and here 4 again. So, and the sum of these 4 values, so how many times each edge was in some path, is equal to the answer we previously calculated in the different way. Okay, now sum over subsets. So there are some competitions with prizes, let's say 2, 5, 3, 10. And the first competition we win with probability 50%. So on average, the prize we get from this competition is 1. If the price is 5, the average we get is 2.5. Just remember about the very first thing, the lottery tickets or coupons. We compute the how much this competition gives us on average. Here 1.5, here 5. And the expected value of the sum is the same as the sum of expected values. So, because linearity of expectation. So the average, well, we'll get 10. I didn't want that, so let's say that here we have, instead of 10, we have 11, so it's 5.5. And now the sum is, I think, 10.5. So this is 4, 5, yeah, 10.5. And this is the answer. And now the idea for this problem is to consider some different approach to be able to apply it later. There are 2 power n possibilities. So here it's 2 power 4, 16. So we can say with a short bit mask, we can say which competition we win and which we don't. So let's say that here we win nothing. This mask means that we win only the last competition, so the one with 11, and so on. And here the total price will be 0, 11, in case of this 3, 14, and so on. There are 16 possibilities. And each of these possibilities has the same probability. So we can just take an average of that. Say 0 plus 11 plus 3 plus 14 plus and so on. And divided by 16. we will get the answer. So it must be also 10.5. And how is it similar to the contribution technique? Well, for every so one approach was for every number to just say what it adds to the answer. This was a very straightforward approach. But also, if we start from this side, from the side of possibilities, and if you want to, for example, find the sum of results for all possibilities, so this number, this sum, then for every number, for example, for a 3, we can say how many times it will be added here. So every time that there is a 1 here at this place, so this competition is 1, we add 3 to the sum. So how many times will 3 be added? Well, it will be added 2 power n minus 1 times. Because among these 2 power n strings, like bit masks, half of them has 1 at this place. Or we can also say, if we want 1 here, so 1 here and here, some other 3 values, there are 2 power n minus 1 ways to choose values here, whether these competitions are 1 or not. So the sum we see here is the sum over 2 power n minus 1 times 3 plus 2 power n minus 1 times 2 plus and so on. So it's the same thing as 2 power n minus 1 times the sum of values 2, 5, 3, 11, and the sum is what? 21. And so this is 8 times 21, and the sum we computed is the same as we have here, and you can see that this divided by 16 will be the same as 21 divided by 2, so indeed 10.5. And let's get back to the statement so we found the expected value of the total won prizes, but the equivalent problem, like equally hard, is find the sum over total price over all 2 power n possibilities and print answer modulo 10 power 9 plus 7, some big prime number, because otherwise the answer can be huge. And this value is just the sum of all possibilities divided by 2 power n would give us the previous answer, the expected value. So we see that these problems are equally hard. If you compute the answer for one, then you can divide or multiply by 2 power n and you will get the answer for the other problem. So often the problem is about expected value, but you should solve it from the side of summing over all possibilities and then divide by 2 power n or maybe n factorial, depending on the number of possibilities for in this problem. Or maybe sometimes the problem says find the sum over all possibilities, and print the answer modulo some prime number, but it's actually a problem about combinatorics and probability, but the author maybe wanted a very good precision. The big difference is that if you are asked to print a real value to the output, so probability of expected value, there is some precision required, and maybe a problem is easier with this precision required, what we will see later today. And sometimes they ask for the sum modulo something, and it turns out to be the same thing. For each bit, add 2 power n minus 1 times value to the answer, exactly that. So now we will use it in two a bit harder problems. Well, first in problem number 4, that is from an actual contest by Google. So this is for math encoder. You are given a sequence of n numbers, and we are going to choose one of non-empty subsets uniformly at random. Find the expected value of the difference between the maximum and minimum element in the subset. And equivalently, so as in the previous version, the difference, the expected value of difference is basically the same thing as finding the sum over possibilities of that difference. And let's first solve it for n up to 2000, and then we will solve it for bigger n. And n up to 2000 we can do in n square complexity, and this is what we will do. So there is some input. By the way, when I think about problems, I like to print some sequence and think with that, and now to draw something, not just to think in my head. So this is something that I would also do during a contest. I recommend that. And if you want to absolve this problem later, you can just Google Code Jam Kickstart 2017 round B, and it will be one of problems. Okay, so there are some ways, there are some possibilities. For example, in subset 2, 7, 4, 3, the biggest value is 7 and smallest value is 2, and then to the answer we would add 7 minus 2. Then in some different possibility it will be, for example, 5 minus 1, then maybe again 7 minus 2, and so on, and the sum of these differences is the answer. But instead of iterating over all 2 power n possibilities, we can iterate over something and count how many times it will appear in the answer, in the sum, the contribution technique. So we can iterate here over pair of numbers, pair maximum minimum, and to think how many times this difference will be added to the answer. Well, if we talk about the solution with finding the sum over 2 power n possibilities, then we should think, let's ignore for now these two here to make things easier. In how many ways, among 2 power n ways, this is maximum and this is minimum? Well, we can also take numbers in between, so 4, 5, 3. So there will be 2 power 3 possibilities, every possible subset of this, such that we will add 7 minus minus 2 to the answer, and so on. So we can just iterate over pairs of numbers, count numbers that are between them, and there are 2 power the number of numbers here, possibilities for that to happen. And if we think in terms of probability, so if we choose a random subset of this, so each number is destroyed, like erased, with probability 50%, and now what is the probability that this will be maximum and this will be minimum? Well, then all numbers smaller than minimum or bigger than maximum must be erased, and the probability for that is 1/2 power the number of numbers smaller and bigger, so here it will be 2. And also we want these 2 numbers to not disappear, so we must multiply it all the time by 1/4 and times 7 minus 2. So this is something in terms of the number of ways, the number of possibilities, and this is something in terms of probability. And actually it's the same thing, because here we have 1 divided by 2 power 4, here we have 2 power 3, and all the time what we add here to the answer will be the number of ways divided by 2 power n. Here it will be 2 power 7. So it's equivalent. So you should, when you solve a problem like this, you should think about whichever approach is easier for you, is more intuitive for you. And regarding the implementation, there are many ways to count the number of numbers in between, but what is useful is to just sort numbers, because the order of them in the input doesn't matter. and if you sort them, then when you iterate over index ij, minimum and maximum, you simply know that what is the number of numbers in between, or what is the number of numbers smaller or bigger. Okay, and one more thing about possible ties. So here we removed 2 to make things easier, and if there are ties, then it's good to it's best to like think about them and to care about them in the implementation, because it makes things uglier in your code. So it's good to think that, let's say that this 2 is slightly bigger than this 2, for example. So let's say that this 2 is like 2 with a plus and this is 2 with a minus. So let's say that every time if there is a tie, we treat previous number, leftmost number, as bigger one. And if we just say that, of course, we don't have to do anything in our implementation about that. We don't have to change this number to some real number like 2.001. We don't have to. It's just that now when we count number of numbers in between, we know what to count and what not to count. And the reason why it works is because if both these numbers are in the taken set, and only one of them we want to treat as minimum, then it's good to say that, okay, if they are both in the set, then we treat this number as smaller, so that we wouldn't have to then subtract something. We want to count every possibility only once. In some problems, you will see that we count every possibility many times. For example, we'll count something 2 times, and at the end we'll have to divide the answer by 2, something like this. But here it's hard to at the end say how many times we computed each thing. Well, maybe we would have to divide the number of, like, when we count the contribution of 2's to the answer, then we would have to divide it by the number of 2's, something like that. It's hard to think about it and to do it correctly. So it's better to decide that ties are decided in some manner, and now to treat them as different numbers. Asymptotic notation, man, your one looks like a carrot. So what looks like a carrot? Oh, you mean my one? Well, I'm not saying I write... I don't write nicely, I agree. And the complexity of... So here first I would solve... I would sort numbers, so n log n, and then I would iterate over pairs of numbers. And then if I sort it, I know simply what is the number of numbers in between or outside the interval. Sort the array, and for each number add number of times it will be maximum times num. Yeah, so Vaibhav gives us a solution for the harder version. First stream by my love Sachin. No, it isn't my first stream. You can see my past streams in YouTube. I had so far 1 stream on Twitch a month ago, and quite a few streams on YouTube. And I stream solving problems from programming competitions, from algorithmic competitions. And as you see here, sometimes I'm going to stream a lecture. I'm going to teach something. Okay, and how to solve this problem for n up to 10 power 5. This is something that Vaibhav said correctly what to do. So let's create a new page for that. When we find the expected value of max minus min, linearity of expectation works not only for addition but also for subtraction, and we can say that this is expected value of max minus expected value of min. And this, computing this, and in the same way computing this, is much easier, because for each number right now we want to count ways where this is maximum, and this is much easier because we just when numbers are sorted, this number is maximum in 2 power 4 ways, because we can choose whether these numbers are taken or not, and these numbers can be taken. And well, our probability that this will be maximum is the probability that none of these numbers to the right are taken and this number will be taken. So linearity of expectation. And also we can think about it as contribution. Now you can see that expected value and contribution are very related. So contribution works because of linearity, let's say. It's the same thing. Because here we can think for each number how many times it will be maximum. So how many times it will add something to the answer, and later also for each number how many times it will be minimum and it will subtract something from the answer. And yeah, so this, after sorting, it will be linear complexity. And the next problem is the same, but it's about intervals, and it's also from a contest. So we have like 40 minutes to the educational round on Codeforces, so it will be good to finish in half an hour. And we have we have 4 problems that I want to talk about for sure. 9 can be moved to the next stream, maybe on Monday. Okay, we'll see. A new page. So the problem is the same as previous one, but instead of iterating over subsets, we iterate over intervals. One more thing regarding the previous problem. Here, if we say that we are choosing one of 2 power n minus 1 non-empty subsets, if you found the expected value of the random subset, then you should at the end, I think, multiply the answer by 2 power n and divide by 2 power n minus 1. Because first we considered also an empty set that gave us, I think, the difference of 0, because there is no maximum and minimum, so we didn't count that. But well, there's some it's some implementation stuff, whether you will have to do it or not. So intervals. This time we can sort numbers, and we are given some sequence. And we must iterate over every interval, and to the answer add maximum minus minimum and find the sum over that. Or equivalently, we say that we choose a random interval, and there I think n times n plus 1 divided by 2 intervals. We're choosing a random interval among those, and we are asking about the expected value of the difference, max minus min. So again, as in the previous problem, it's enough to just find the expected value of the maximum, and then separately for minimum, and then subtract those. And so let's think in how many intervals this number is maximum. Then to the answer we will add 5 times the number of ways, or the probability that it's maximum, and we will print the sum over those products, and that's it. And in how many intervals this 5 is a maximum? Well, this interval must start somewhere here. So 8 is a bigger number, And this interval, if it also contains an 8 or something to the left as well, then 5 will not be maximum. And similarly to the right, 7 is the next bigger number, so the interval can't contain that. And if the first number is one of these three, and the last number is one of these two, then the interval contains 5 as a maximum. So for every number, the task is to find the previous and next bigger number, and these ways will be, so 5 is the value, AI, and as L and R, we denote the length to the previous bigger number, and R, the length to the next bigger value. And to simplify the implementation, in case there is no bigger value to the right or left, we can add infinities as 0th and last element, just to make the implementation easier. Because then, for example, for 7, we'll say that the next bigger element is this infinity, so we must end interval up to this point. What is okay? We indeed must end up to this point. Okay, and once again, we will not go deep into the implementation of this because it's some, I don't know, data structure problem, but in short, you can, for example, go from left to right, store numbers in some segment tree or a set, and for a number, we ask about the smallest length to the bigger number. So among numbers bigger than 5, we ask about the rightmost number, the last number here. And it can be done in some ways. But also, it can be done in linear complexity. If the input numbers are permutation from 1 to n, and this is an extra task for you. So there are a few ways to do it in n log n, but there is maybe only one way to do it in linear complexity. And to approach that, I recommend imagine sorting numbers from biggest to smallest, for example. So let's start with 8. And now for 8, we know that the length to the next and previous bigger number are just length to the beginning and end of the interval. And then after considering 8, we remove it, like we mark this cell as containing a big number, and we'll move to the next number, so 7 here. Then in some structure, we ask about the previous and next bigger number, so we know that, and then we remove, and so on. So at every moment in some structure, we store positions where big numbers are, and when we have a new number, we just ask about some lower bound, for example, in set. But the question is how to do it linearly. Farbot Sam, Hadi, please talk English in the chat. Next problem is randomizer. So the previous problem, imbalanced array, was from Codeforces educational round 23, and this one is also from a contest from Codeforces round 313. So I wonder what is the current numbering of contests. It's like 519, so it's a long time ago. Randomizer. You're given a convex polygon with n vertices. We choose a random subset of vertices, what gives us a new small convex polygon. Find the expected value of the perimeter of this random polygon. So we are given a polygon, convex polygon, with n vertices, and there are two versions of this problem, either up to 2000 or up to 10 power 5, for example. And now there are 2 power n possibilities to choose a subset of vertices. And if we choose some vertices, then we connect them into a new polygon. It will also be convex. And we ask about the average perimeter of that, expected value of perimeter. And the perimeter is the sum of lengths of segments. I think it can be done in O of n, even if numbers aren't permutations ones up to n. Possibly, I think that with some trip or something, it's possible to do it. But like, there is a solution without, let's say, without a tree. I don't know if then you can solve it. So, like, it's not about just sorting a permutation fast. So here numbers are from 1 to n, so that we can sort them in linear time. But yeah, what about the rest of the problem? Histogram approach. I think you are correct. I think that this is exactly what I meant. So, but let's leave the details for others to think about, like, as homework. Okay, back to the polygon problem. So we can say that every point dies with probability half, and the remaining points create a new polygon. And how to solve it? So just I will give you first 1 minute to think about it, to think how to use the contribution technique to find the expected value of perimeter. And time is up. And since today a lot of times we deal with sums, and I already said that perimeter is sum of lengths, we can say that this is expected value. Also, expected value is printed without v, like to make it a bit shorter. Also sometimes without brackets at all. So this is expected value of the sum of sum of lengths. So this is, let's say, L of I is length of each next segment, and this will be equal to the sum of expected value of length, because linearity of expectation. So for every segment, if it appears as a segment in the polygon, then it adds its length to the answer. So what we will do is we will iterate over pairs of vertices. So this time pairs of vertices. This is why we'll get complexity n square. And when we have some vertices, ij, then we want to know either the number of ways, or in other terms probability that this segment will exist. So for this segment to exist, we need these 2 points to survive, so probability 1/4 times either all points here are destroyed, so this segment will have all the polygon to the right, everything will be here. So the property of convex polygon, also if someone doesn't know convex polygon, this is not convex polygon, so because it has like a hole. Something like this is convex. something like this, is concave. Okay, so the property of every segment of convex polygon is that all other points are on one side, for example here. So if the number of points here is j minus I, or maybe j minus I minus 1, I think, so the probability that all of this will be destroyed is 1 second power j minus I minus 1, plus the probability that all points here will be destroyed. And this is 1 divided by 2 power something like, I don't know, n minus this plus minus 1. Let's say plus minus 1 or maybe 2, something like this. So this is probability that this segment will exist and all other remaining points are on this side. So all these 4 points must be removed. And so this is probability that this is a segment in the final polygon, and multiplied by length of this polygon, this segment, we can now, this is the contribution this segment gives to the answer, and the sum over that is the answer. A segment between points I, j contributes if I and j are alive, but every point between them in that last one direction died. Exactly, Anton. Sorry I read comments like this so late. I see that you wrote that 3 minutes ago and you knew a solution, but anyway, I'm still showing this solution. It's better if I do it my way, and instead of reading comment and then repeating the same thing. It doesn't matter much. But yeah, you are right. So for each segment we computed probability that it will be counted in the answer, and we multiplied this probability by its length to know how much contribution it gives to the answer. And what about this bigger n? Well, since we are running out of time, I will quickly say that. If polygon is huge, and n is 1 million, then likely a segment like this will not appear, going through the middle of a polygon, because the probability of that is something like 1 second power n divided by 2, something of this magnitude, because all points here would have to be removed, and it's almost impossible. If we want to print the real value as the answer, so with some precision, like 10 power minus 9, then we can discard those segments that have probability smaller than, for example, 10 power minus 18. Those don't count much, don't matter much. So actually in the very big polygon, we'll only consider segments from a point to the next point, and so on. And let's say that something like 50 next points should be considered. So segments between I and J, such that the distance between them, the difference of indices, is up to 50, because those pairs of indices that are further away have too small probability of giving something to the answer. So their contribution will be very small. And this is how we solve it with probability n times 50, let's say. And that's it about this problem, randomizer. Also, in the problem from Codeforces round D, that 313D, the problem was a bit harder because we had to compute the area, not perimeter, and also we had to use something that is called Pick's theorem, but it's just an interesting fact for you if you want to solve this problem. But then it's more geometry. I changed it to perimeter to only show the contribution technique and not to focus on the geometry part. And we'll solve 2 more problems. The next one being random convex hull, so still something related to geometry. Random convex hull. You're given endpoints. No 3 points are collinear. Each point disappears with probability 50%, as in the previous problem. And find the expected value of the size of the convex hull of all remaining points. So let me change the color back to black, so it would be more visible. We are given some points. No 3 are collinear, so we shouldn't have to worry about it in the solution. And some subset of points will be chosen. Well, for a moment, let's go back to green. Some subset of points will be chosen, and we are considering a convex hull of those. If you don't know what a convex hull is, then this problem is too hard. So just wait for the next problem, I guess. But in very short, for a set of points, convex hull is like putting a rope around those points, covering them from outside. So points in the middle don't count at all. So this is convex polygon with smallest area that contains all the points. This is the formal definition. Okay, so back to black. Here, so actually this problem might be easier if we say that we want to find the expected value of the perimeter of such a convex hull of random subset of points, because then we can iterate over each pair of points, so a segment possible. Then the probability that it will be a segment is the probability that points on one side, let's say that there are points on the right side, L points on left side. So again, the probability that this will be a segment of convex hull is 1/4. These two numbers might stay, not removed, times half power R plus half power L, the same way in the previous problem. And if we ask to find the expected value of the perimeter, we would find the sum over this multiplied by length. But here we just multiply this by 1. The contribution technique is about iterating over some element and counting how many times it will appear in the answer. Here, for every convex hull, the size, so actually once more, we are finding, where is it? We are finding the expected value of the size of convex hull of remaining points. Size meaning the number of vertices. Well, it also is equivalent to counting the number of edges. So for this convex hull, we would get 4 to the answer. Sorry. And well, once again, for each edge, we count how many times it will appear in some convex hull, and this is how much it will add towards the answer. So actually, the answer is the sum over segments between some points I, j over this value. And that's it. We only have to compute R and L, and we will not focus on that in this stream because it's just some geometry. For n up to 200, you can do n cubic. So iterate over segment, then iterate over every other point and check if it's on the left or right from the segment. So left or right from line, like extended segment. And to get a solution for bigger n, then we want n square log n. You have to, from every point, sort other points by angle and do something like that. So it's a bit hard. Also, once again, I'm not focusing on that today. And an alternative approach is to, for every point, so for every vertex, count how many times it will appear as a vertex of convex hull. And then we must count what is the probability that all other points are, like, for some points, the probability that this will be in convex hull is the probability that all other points are on one side of some half plane. And if you sort points by angle, it will be possible to solve. But that's only some short explanation. Approach for n up to 10 power 5. I'm glad you like the approach. Would anybody like to practice algorithms with me later? Nope. So, Jake Walker, I recommend you visiting my, well, not my, the competitive programming Discord. The link is in the description under the video. And there you can try to find someone to practice together, or to just, like, I don't know, ask for problems, etc. So Discord, I think, is a perfect place for that. It's a competitive programming Discord that also has a sub channel for my YouTube stuff, and we can talk about my videos there. But also there are many other sub channels in this competitive programming Discord. Okay, so we covered the geometry problem, and now the last problem for today. Also, the educational round starts in 12 minutes, so get ready for that. And the last problem, so let me, eating ants. Let me change the title. Eating ants. We are given a sequence of length n. Once again, there are two possible versions. The harder one will be harder. And let's focus on n up to 2000. And n minus 1 times someone will remove the first or the last element, each with probability 50%. What is the expected value of the last remaining number? A new empty page. So we are given some sequence of numbers. And in first step, either 2 or 8 will be removed, each with probability 50%. Let's say that it's 8. Now, again, first or last element is removed. Let's say 3, then maybe 2, maybe 7. And in this case, we have 5 as the final score. And we are asked about average final score. So, of course, you might already guess that we will iterate over I. For example, so what about this 5? We iterate over I with for loop, and we find the sum of probability that I will be the last element times the value of I, times AI. And this will be the expected value from the definition. And now the problem is how to find the probability. So to say it quite fast, if every moment we remove something from left or right, and we want to remove, so let's say that there are L numbers here and R numbers here. So the problem becomes something equivalent to L plus R times we choose 1 or 2, so end or start. And we want to get L 1s and R 2s. And if you are familiar with that, you should recognize that it's like the number of ways for that is L plus R choose L. So L plus R factorial divided by L factorial R factorial. Or you can also think about it this way. You are in, let's say, infinite grid. You start from top left cell, and each time you go 50% to the right and 50% down, for example, following this pattern. And after n-1 steps, we want to be at some exact cell. And the numbers of ways up to this point is exactly like binomial coefficient. So here, this probability is, I think, n minus 1 choose I minus 1, so this is value of L, divided by 2 power n minus 1. Yeah. So this is the number of possibilities, how the process will look like. And this is the number of possibilities such that I will be the last element. And the easiest way to compute this is to just compute factorials, but the factorials could be huge and the precision, like long double in C++, likely will not be able to hold that. It's too big of a number. So it's slightly better to just try to compute it's called, I think, Pascal triangle, the values of binomial coefficient, something like this. It's very easy dynamic programming. So like with a simple formula that n choose 4, n choose k is equal to n minus 1 choose something plus n minus 1 choose something. So there it's easy to compute dp of nk, to compute all values n choose k. Also, numbers here will be big, but if you compute probability immediately, so you compute not really this value, but this value divided by 2 power L plus R, then the precision will be okay, because your values will be from interval 0, 1. So you want to get values from interval 0, 1. So of course this is a very short explanation, but it's because stream is quite long already and there is an educational round coming up. And also there is a version with n up to 10 power 5 that is harder to get, especially because of precision. So then we should focus on computing something like this, the ratio of fractionals, and it's just harder to get. But today we care about the contribution technique, and the most important thing you should remember is that the main point of the problem is the fact that we should compute this. This is what you should understand from reading the statement, that we should find the sum over probability times the value. And the last problem you can read later and try to solve it, because it has a lot of solutions, also some simpler ones. And also it's with contribution technique, so for every number how much it adds to the answer. And we will talk about some possibilities on the next stream on Monday, the same time. But also there is some hard way that will show us how to solve much harder problems that we will cover on Monday. And yeah, try to solve some bonus problems here from the problems. So for example, we didn't cover problem 8. Yeah, here's another bonus, so you have a lot of things to do if you want to go deep into those problems. And that's it. We see next time on Monday, same time, so 2 p.m. European time, CEST time. Thanks for the stream. Looking forward to more of this. Gotta go for now. Yes, see you, Vibe. You missed like what, 5 minutes? It happened again. I remember some other stream where when someone said that he must go, so he watched for the whole stream, and then I noticed his message when I had to go myself. Good luck in the educational round on Codeforces if you participate in that. And if you like this content, consider liking the video and subscribing to this channel so you'll see my future videos. Also, if you use Discord, see in the descriptions link for Discord channel. And if you use Facebook, you can see my channel as well, where I sometimes put my thoughts about contest, or I put some short problems, sometimes with solutions. So just some channel to hang around. Thank you a lot for watching and for reading my not really beautiful writing skills. And see you on Monday. Bye bye, good luck in the Codeforces round.